Hi, my name is Swapnil Patel, and I'll be talking about our ongoing research on building scalable directories for shared file systems. This is joint work with Garth Gibson at CMU. So today, the demand for scalable storage systems is increasing rapidly as more and more applications begin to harness the parallelism of big computers like massive compute clusters and cloud computing infrastructure. Large file systems do a great job at scaling the data path. What I mean is file systems, specifically cluster file systems, use techniques like striping and sharing resources across multiple servers and object-based storage to scale the performance of operations performed on file data. In addition to that, these file systems enable highly concurrent access to the file data using sophisticated locking mechanisms and distributed cache consistency schemes. However, large file systems haven't focused a lot in trying to scale the metadata service for file systems. So in this talk, I'm going to focus on one kind of metadata, which is file system directories. I'm going to show you how we can build directories that can store billions to trillions of files in every directory and be able to handle a high degree of concurrency in terms of inserts and lookups. Our goal here is to build file system directories, and when I say file system directories, what I'm trying to say is that we want to maintain the Unix file system semantics, and we want to support the VFS interface. So there are two trends that motivate the need for scalable directories. The first trend is that file system vendors and users are seeing an increasing number of applications that use the file system as a fast and a lightweight database. Typically, this happens when you have lots of clients trying to insert small files at high speeds in a single directory. These kind of applications are common in scientific experimentation and high-performance community, as well as data analysis for post-processing. One such example is poor process checkpointing of large applications. So imagine an application that runs on a big cluster of thousands of machines and is executing with thousands of parallel threads. When this application decides to take a checkpoint, what happens is it dumps all its state from the memory onto small files, and all these thousands of execution threads insert these files in a single directory. As a result, what you want is the directory subsystem to be able to handle these high degree of concurrent inserts in that directory. So there are a few other applications in where you can see a steady rate of creation inside a large directory. These applications are common in internet services or long-running scientific experiments. For instance, you can imagine a small kilobyte-sized record associated with every URL, which you use later to do some post-processing. The second trend that motivates the need for large directories is the increasing application-level parallelism. So applications today are beginning to run on large compute clusters. Today's cluster consists typically of thousands of nodes. Slowly, this number is going to tens of thousands of nodes. And with the increasing use of multi-core machines, you can imagine that applications in future would end up running on hundreds of thousands of execution threads. At this high level of parallelism, it's important that the underlying file system, and more specifically the metadata services, be able to sustain the desired scalability. So what we decided was, OK, let's go ahead and try to come up with a solution by which we can support really large directories. And the central tenet of our research is extreme scalability through high parallelism. So we built a distributed indexing technique, which we call GIGA+. And what this indexing technique does is it allows highly unsynchronized and parallel growth of the directory over a scalable number of servers. And this growth happens in a completely decentralized manner without a coordinator. In addition, we also support classic requirements like incremental growth and load balancing across the number of servers that you're using. The second key property of our system is that we tolerate the stale mapping information at the clients. This allows the clients to use the system at high speeds, and the servers can update the clients on demand in a lazy manner. Finally, we use a unique self-describing structure which uses a bitmap, which allows us to encode the entire index in a highly compact representation. So before I get into the details of our technique, let's take a look at the current state of the art in directory indexing and how the large file systems today implement directories. So when we first think of out-of-core indexing structures, two things come in mind: hash tables and B trees. File systems have used both of them. SGI's XFS uses B trees for its directory implementation. Linux ext2, ext3 uses a modified version of a hash table to implement directories. So what are the desired properties from any indexing structure if you want to build a scalable system? So the first property is load balance key distribution. What we want is, if you're using a number of servers, we want to distribute the load in terms of capacity and performance across all these servers. So by simply hashing the key, if you use hash tables, hashing the key gives you this property, assuming that the hash function is fairly random and distributes the keys uniformly. The second key property is incremental growth of the directory. This is particularly important for file system directories because most directories in any file system are going to be small. Some of them grow to extremely large sizes. Hence, we don't want to penalize the performance of small directories. However, classic hash tables, the traditional data structures 101 hash tables, don't support incremental growth. The problem is that in a hash table, you divide the key space into a fixed number of partitions. And once a single partition gets filled up, you have to go and rehash all the keys into a bigger hash table. Clearly, that's an infeasible approach if you have billions to trillions of keys in a single directory. There has been decades of work in trying to make hash tables grow in a dynamic manner. And one of the classic work in that is extensible hashing. So the key idea of extensible hashing is to grow the hash table one partition at a time without actually rehashing all the keys. Let's take a look at how extensible hashing works in practice. So this figure here shows how extensible hashing works, where what happens is in extensible hashing, you add a layer of indirection, which we call the header table. Essentially, this header table holds pointers to the different partitions where the keys are eventually stored. Each entry in the header table points to a single partition, but different partitions could be pointed to by different entries in the header table, as I'll show soon. So once you have lots of entries in this header table, you need to use a suffix of the hash to decide which entry to point to. We call this rbit suffix as a radix. And for instance, in this case, since the header table just has two partitions, we use 1-bit radix. And this 1 bit helps us decide whether you want to go to the 0th bucket or the first bucket. What happens when the partition gets filled up is the header table doubles in size. So what you have is increased size of the header table, where initially the new entries point to the old partitions. So when this happens, what you want is you want to increase the number of bits that you're going to use from the hash table to decide which of these entries in the header table is the correct entry. So we increase the radix by 1, use 2 bits to decide which of these 4 entries should hold this particular key. And in this case, for example, it happens to go to the 4th entry, and the 4th entry currently points to a partition. If that partition gets filled up, you split the partition into 2, create a new partition, and move half the keys from the old partition onto the new partition. Once this happens, you update the pointers of the header table to point to the new partition. So the key idea here is that this extra bit of radix helps you decide what keys move from the old partition onto the new partition. The key drawback of this mechanism is that it was designed to be a single server implementation. What it means is that everything, the header table as well as the partitions, are stored on a single server. As a result, all operations on this hash table are going to be serialized, and the scalability is limited by a single server. So let's look at how current file systems implement directories. Most file systems implement directories on a single server or a single machine. The common way to get access to multiple directories stored on different servers is by using NFS, where you can just mount different directories stored on different servers on the client namespace and get access to those directories. But the problem is that the directories themselves are still stored on a single metadata server. So that's still a potential source of hotspots in a big system. Cluster file systems take a step further. They have two kinds of servers, an I/O server and a metadata server. The I/O server is used to stripe the file data across multiple I/O servers, and the metadata server stores all the metadata. One such file system is the Lustre file system, which is now owned by Sun Microsystems. What Lustre does is it uses a single metadata server to store the entire directory tree and all the metadata associated with the files. As a result, all metadata operations get serialized, and you have a potential source of bottleneck in a large system. PVFS is another open source parallel file system used in a lot of real world HPC deployments. What PVFS does is it distributes the directory hierarchy across multiple metadata servers. But the problem is that every single directory is still stored on just one server. So you still have this issue where if a directory becomes big, you're still going to hammer on one server. The state of the art in distributed directories is IBM's GPFS. What GPFS does is, in addition to striping all the file data on the cluster nodes, it also stripes all the directories. So if a directory grows big, it will stripe it on multiple servers. So the way it grows directories, it is using the classic extensible hashing scheme, and it also enables concurrent access to the directories using a sophisticated distributed locking and cache consistency mechanism. Let's look at both the issues. The first issue we should look at is how GPFS enables concurrent inserts in a single directory. So GPFS is a symmetric file system. So you have a node which can act as a client and a server. So if a particular node wants to operate on a partition of a directory, it gets a write lock on that particular partition, caches it, and does all its operations. So here's an example where you have two nodes trying to insert concurrently in a single partition. Initially, in the first step, node 1 has the write lock on the partition, and node 2 comes along, and it says, I want to access this partition. The node 2 sends a request to the lock server for a write lock. The lock server responds saying that, oh, I don't have the write lock is already being taken by node 2, go and contact node 1. So node 2 sends a message to node 1 saying that I need a write lock on the partition that you hold. Node 1 says, fine, I'm not working on it. It flushes the contents of its cache on the disk, which is in a shared disk storage, and sends a response back to node 2 saying that, here, have the write lock and do what you want to do. Node 2, on receiving the write lock, reads the fresh copy from the disk and caches it and performs all the operations. So what's happening here is that on every insert, there are two sources of bottlenecks. First, you have to go and talk to the lock server every time that happens. That's a potential source of contention at the lock server. And second is the disk I/O bottleneck. So for every insert, a client is going to, the holder of a write lock is going to flush its copy to the disk, and the reader, the new holder of the write lock, is going to read it back from the disk. So you have two disk I/Os, at least two disk I/Os happening in every insert. So the second property, the second source of synchronization in GPFS is the way you ensure this mapping of a distributed directory. So if a directory is striped on 3 servers, let's assume this is a directory which currently has 3 partitions, P1, P2, P3. How do you find out what server stores what partitions? So the way GPFS maintains this mapping is that it stores it in the inode of that directory. So the direct, indirect, and double indirect pointers hold addresses to these particular partitions. So as the directory grows, new partitions are added and the inode is updated. But what happens is this copy of an inode, GPFS uses a strong consistency on this copy of the inode. So if there are thousands of clients working on a single directory, everybody will have this copy in cache. So if the directory grows and even a single pointer is added, the splitter or the node that created the new partition has to go and invalidate the cache for all the rest of the clients, update this inode, write it to disk, and then notify all the clients to go and fetch it back from disk. And that's a possible source of a big bottleneck in terms of workloads that have a high degree of concurrent inserts. So the key benefit of GPFS is really great at workloads that have lookup intensive operations. So because there's heavy caching, so you can benefit a lot from caching. You cache all the small directories that you have, and everybody holds a read lock on that and performs all the lookup operations. That's great. That gives you extremely high performance. But as I described earlier, the concurrent inserts are expensive because of two sources of bottleneck. So we spoke with the GPFS developers, and they acknowledged these issues with the concurrent insert workloads, and the current versions of GPFS are trying to overcome these issues in concurrent inserts. However, we still have this residual issue of trying to have a synchronous copy of the mapping information in the system. And I'll focus a little bit more on that. So let's try to think of ways about how we can scale beyond GPFS. GPFS does a great job at scaling. Now let's see how can we overcome the problems with GPFS itself. The first way is, okay, we know that the lookup mechanism is a problem. So let's not use any partition to server mapping. What we can use is a well-known mapping scheme that is known in advance. That is, you don't have a symmetric system. What you have is certain nodes that are going to act as servers, and all directory operations go to those particular servers. As a result, you don't have lock contention that happens in GPFS. And I believe the GPFS developers are looking into such a scheme for their next version. The second problem is we could this mapping issue, and we could just use stale mapping information at the clients. We don't need to keep a consistent updated inode every time. What we can do is, since we know that some nodes are going to act as directory servers, clients continue to use their stale information and send the request to a server. If that happens to be an incorrect server, the server can update the client in an on-demand manner. Just as a side note, there is this indexing scheme called LH star, which enables some of these properties discussed above. But the problem with LH star is that it imposes a strict order in the way partitions are going to be split. And because of this strict ordering, you cannot have any parallelism in that indexing scheme. At any given point, there's only a single partition that will split, and the rest of the system has to wait for that split to complete. So having discussed the issues in current state of the art, what's new in our GIGA Plus directories? So we have 3 new features. First, we eliminate all the serialization in the system. The way we do that is by allowing all the servers to grow in an independent manner in parallel without using any central coordinator. The second key feature is that we don't have any synchronization or consistency bottlenecks. That's because every server only keeps track of a local view of the directory. The directory is partitioned across multiple servers, and each server keeps track of its own partitions. They do not talk to each other when they want to grow. And the third feature is that we use weak consistency for the update messages. So what I mean by weak consistency is that whenever an update happens, it does not need to be propagated to the rest of the system. However, applications that use the directory are always going to see a consistent image of that directory. So by using this mechanism, we can tolerate stale information at the clients, and the servers can lazily and on-demand manner update the clients. Now let's look. I'll give you a quick example of how all these 3 features work together in practice before getting into some of the indexing details. Let's take a look at this example. You have a directory foo, which is divided across 3 servers. Currently, this directory has 3 partitions, P1, P2, and P3. And each partition holds a particular range in the key space. So for instance, P1 holds the first half of the range, P2 holds this next quarter, and P3 holds the remaining quarter of the range. And since you have the directory striped on multiple servers, you need a way for clients to look up a partition on a given server. And for the sake of simplicity, let's assume clients use a partition to server mapping scheme. So client B comes along and wants to insert a particular file in this directory. It hashes the file name, and this hash value determines that this key is going to be inserted in partition P3, and it sends the request to server R. The server R, on receiving the request, can either just insert it in the partition and respond back to the client, or it might split because the partition gets filled up. So when this split happens, server R will contact another server to create a new partition and move half the keys from the old partition onto the new partition. Thus, the key space is divided into half across these 2 partitions. The key thing that happens is that every server keeps track of how its partitions are growing. So when this split happens, server R keeps a split history associated with P3. So what this split history record indicates is that, okay, P3 split into a new partition called P4, and that was stored on server Y, and some additional information like timestamps or other bookkeeping information that you might want to keep. After this operation is completed, the server responds to the client, and the client updates its mapping information. Now note at this point, client A and client B have diverging copies of the mapping information, and that's what I mean by weak consistency. Whenever an update happens, not all the clients know about it, or they don't need to know about it. So the client continues to use its old mapping information and decides to look up the same file, F1, and since it has an old mapping information, it sends the request to server R. So when a server R receives this request, it realizes that it no longer holds this particular file, and that's because a split happened in the past, and it moved half the keys onto the new server. When this happens, the server R uses its split history that we recorded and sends an update message back to the client. So what is happening here is the cost of tolerating the stale information at clients is that you have a few extra hops, few extra forwarding messages before a particular client request hits the correct server. And as I'll talk about it later, depending on how much information you send when you're trying to update the client, this forwarding cost is extremely low. Plus, you can also use techniques, sophisticated techniques like gossip protocols to make sure that servers periodically exchange messages so that everybody has a consistent image. But we haven't looked into that because we're still pondering over the complexities of those, and we really don't need it inherent for our basic scheme. So there are two main questions. Let's get into some details now. So there are two main questions here. First is, how do servers keep track of all the partitions they store? And second is, how do these partitions grow on any given server? So we use a unique bitmap representation that allows us to store the information about the presence and the absence of a partition on any given server. So in this bitmap, a bit value of 1 indicates that a partition is present, and a bit value of 0 indicates that a partition is not yet present. So servers use this bitmap to keep track of all its partitions. And by partition, it means when I say servers keep track of only its partitions, what I mean is the servers don't talk to, whenever a server decides to create a new partition, it does not talk to the rest of the servers in the system or update the rest of the servers. These bitmaps are also used by the servers to provide the clients with lookup hints. When clients receive these bitmaps from different servers, what they do is they simply merge all these bitmaps, which is a simple OR operation, and what they have is a complete map of all the partitions in the index. And they use this bitmap as a way to look up the mechanism. So in the previous animation that I showed, the partition to server mapping, we don't need to keep that mapping. It's simply this bitmap that allows the clients to deterministically look up a partition and the server that stores that partition. Let's take a quick example to see how bitmaps actually work in practice. Let's assume this is a bitmap. 1 indicates a partition is present and 0 indicates a partition is absent. You're trying to look up a particular file. You hash the file name, and you see that the hash tells you that it's indexed on the partition, which is pointed to by the ith bit location in this bitmap. You see that the bit location is 0, which means that the partition is not yet existing. So what you do is you divide this location I by 2, and then look at that particular bitmap. Once you look at that index, you again see that it's 0 and it does not exist, and you repeat the process. And you continue until you hit the first location, which indicates that the bit is 1. That means the partition exists, and you go and send the request to that particular server that holds the partition. So using this bitmap representation has a couple of benefits. First, it's a highly compact representation. For instance, a directory with billion entries can be stored in less than 16 kilobytes. So even if you have lots of huge directories in the system, you can easily always keep this bitmap in memory at most times. And since it's small, it's very low overhead to send it across the network. The second benefit is that the entire state of the server is encoded in this bitmap. So when an index decides to grow, what it does is the server just simply updates its bitmap about the new partitions that are created. It does not need to talk to any other servers or exchange the bitmaps explicitly with any other servers. And the servers also use these bitmaps to update the clients. So when a client receives an update message, it essentially receives the bitmap from the server. And since this bitmap has information about all the partitions on the server, you are sending a lot more information to the client than what it needs. So since the client gets so much information, the possibility of it being stale for a long time goes down significantly. Now let's look at the second issue, which is how do you partition a directory across servers? How does the directory grow? How does the index grow? Let's take a look at this quick example. Imagine a directory. Directories start small. Most of them are small. Initially, there's a partition which holds the entire key space. This partition receives an insert. If this partition gets filled up, it splits into 2. So what's happening here is the directory, the key space is split into 2, and you have a new partition created on another server. And similarly, you get another insert which happens to go in the second partition, and it splits into 2. So what's happening here is every partition is splitting independently. In the traditional extendable hashing scheme, whenever a growth happens, you have the tree grows symmetrically. That means whenever you add a new level, new depth to the tree, all the nodes are added. In this case, that's not happening because every server makes an independent decision of splitting a partition. And this goes on further. So what we achieve is highly concurrent growth without any synchronization in the system. And in addition to this, servers, as I said earlier, also keep a split history associated with its partition. So in terms of the tree representation, the nodes, the pointers to the children node essentially capture the split history of that particular partition. So what happens is you use those split histories to correct the clients that have stale mappings. So one way to look at this split history is that they give you a complete history of the growth of the directory as a transitive closure. So what I mean by that is if you go to any partition and traverse its split histories, what you're going to get is the entire partition, all the partitions in that particular directory. And we can simply encode them in bitmap as well as keep them as an attribute of a partition. The cool thing about these split histories is that it allows us to reconstruct the bitmaps. So if a server goes down and comes up, if there's a crash and reboot, you can simply just traverse these split histories of the partitions and recreate that bitmap without actually contacting any other server. And we use them to update the stale information at the clients, as I said earlier. So the key elements of our GIGA Plus design are completely decentralized and parallel growth, and the fact that we tolerate the use of stale information at the client's end. Now let's look at the evaluation of some of the core indexing properties. There are 3 goals of this evaluation. First is we want to check the overall scalability of these indexing structure. We want to see the cost and the benefit of using weak consistency, and we want to see the trade-offs in choosing the right partition size for a directory. We model clusters up to tens of thousands of nodes. Our server model is simple. We use a local file system with a 64 MB directory entry cache and 2 disks on every server. The disks are modeled using a Seagate Barracuda model with 5 millisecond seek latency and 300 megabits per second X for transfer time. The network is modeled using a gigabit Ethernet. We associate a cost of 1 millisecond to insert a directory in a partition. And clearly, it seems like, so what it means is a disk can handle 1,000 I/O operations per second. It's faster than what most disks today can do, but it does not affect our scalability issues here. So what this graph shows is basically that, yeah, our indexing scheme achieves linear scaling. What we tried to do here is that we have 1,000 clients trying to create 10 million files in a single directory striped on a varying number of servers, and with a partition size of 10,000 entries in every partition. As you can see that whenever you double the number of servers, you see a 2x improvement in the sustained throughput of the system, sustained insert rate of the system. The second experiment we ran was to compare weak consistency with the strong consistency semantics. What we compared with is an improved version of GPFS. As I mentioned earlier, GPFS is trying to fix the synchronization issues with concurrent inserts. So we used an advanced version of GPFS that will come out soon that only has a problem of consistency when the bitmap changes or when the mapping information changes. We compare it with our GIGA Plus model, and what we see is that the amount of data moved by GIGA Plus is much lesser than what a strong consistency protocol will do. We can see at least an order of magnitude difference in terms of the bitmap, the mapping information that is sent across the network. The third and the final aspect of our evaluation was, let's see how readdir performs. It's an important operation where you want to go and look at all the entries in a particular directory. And readdir depends on the size of the partition. So we varied the different we played with different partition sizes and tried to understand what's the overhead of using small partitions or big partitions. So using small partitions, the problem with using small partitions is that you're going to pay a heavy readdir latency. And the reason that happens is readdir goes to every server and reads this small partition. So effectively what you're doing is you're going to the disk, reading a small amount of data, and your bandwidth effective utilization is dominated by disk seeks. As a result, your parallel readdir is going to take a lot of time to complete. And clearly, since the partition size is small, partitions are going to split more frequently. As a result, clients are going to get out of date faster, and you're going to send the bitmap across the network a lot more than you should. So you'll see almost 3 to 4 orders of magnitude more bitmap traffic for a small partition compared to an extremely large partition. That does not mean that we could just use large partitions. That's because if a partition is large, it's going to take time to get filled up, and therefore it will be slower to split. So you won't be using all the available parallelism in terms of the number of servers very quickly. So it will take time to insert a whole number of entries in that particular directory. So in conclusion, if this talk was 1 hour long, what I could have told you is basically that there are 2 prototype implementations that we are working on. First is in the PVFS2 parallel file system, which is an open source cluster file system. We're working with the PVFS developers. Currently, the code is still in a graduate student version. So if the code, once it becomes stable, there are chances that we might merge it with the main PVFS line. We are also implementing a user level implementation in Fuse. The goal of this implementation is to create a vehicle to play around with ideas with scalable metadata and directories and large directories. We're also working on trying to come up with schemes to handle the operational realities of any large system, like handling server failures. We have a novel replication scheme that tries to improve on the classic chain declustering model. What our replication scheme does is it gives you highly parallel and fast operations, both in terms of failure and data recovery. Plus, we are working on things like what happens when you add and remove servers from the system, and other issues like handling overloaded servers and DHCs. I'll be happy to discuss these issues offline. So finally, the key takeaway message from our work is that today's file systems don't do a good job in scaling for large directories. So what we came up with is a POSIX compliant file system directory idea, which has 3 key properties. First, we achieve highly concurrent growth with minimal synchronization. We don't have any serialization in the system and allow the servers to grow their state independently, because each server only keeps track of a local view of the system, and there's no global shared state. And finally, using weak consistency semantics for the update messages, we can tolerate the use of stale mapping information in the system. Thank you, and I'll take questions.